Did you go to Hajj?
We have a Dave and Buster's there too.
All right, ready to get started? Yep. Everybody's in the back row, except for these. And I've got this strong contingent in the back. In fact, that side of the room. All right. So, were there any questions about logistics or anything before we jump into the material? You all are off next week, and then I'll see you 2 weeks from tonight. Your Blackboard's going okay, submission, all that stuff is working out?
Yep.
All right, fantastic. So we'll start tonight with hypothesis testing. I think hypothesis testing is great, and it's a great way to make some sense of what we've learned so far. Does everyone have a finger?
No.
Sure.
Oh, okay.
You got it? Okay. Everyone is welcome in class. So, all right, so hypothesis testing is great because it links statistical theory with just common sense questions. How it works is we'll pose a hypothesis. We'll say, I think the machine is operating at a low error rate. Or we'll say, I think the proportion is 42%. Or I think the average income is this amount. And then we'll look for evidence to confirm or refute that hypothesis. And when we look for evidence to confirm or refute that hypothesis, that's when we do the statistical theory that you all have become familiar with over the last 3 classes. So we'll use that information to answer a very straightforward, common sense business question. Because when you set up the hypothesis test, you want it to be something useful. So I'm asking this question, and I want to answer to it because it helps me business-wise or it helps me in some other way. And you're going to use the statistical theory to answer that question. So it is the link between practical business applications and statistical theory. So, I think it's great. With that, I will jump in to the content. Oh, thank you very much. So, I'm going to work through some of the exercises in the textbook. I'll start with exercise 9.6 if you'd like to follow along. Not necessarily that you follow along, but if you'd like to follow along, it's 9.6. So how this exercise goes is we are looking at 1-bedroom rental apartments in St. Louis. And we're talking to a realtor. And the realtor tells us, I've got an average price of 1-bedrooms, or there's an average price of 1-bedrooms in St. Louis of $1,560. So this realtor says the population mean of 1-bedrooms in St. Louis is 1,560. So maybe we get a little bit of a weird feeling about this realtor. We think the realtor is lying to us for some reason. Just it's kind of shady, he's trying to sell something. We're not really confident in what the realtor says. So we want to test that. And we want to find some evidence to see if we can support what he says or possibly refute what he says. So we decide we want to be scientific about this. And we say, let's give the realtor the benefit of the doubt. Let's assume that this is true. Let's call this a null hypothesis. Let's label it H and a little 0. All right, that's our symbol for null hypothesis. We're going to assume what the realtor says is true, and we're going to look for evidence to the contrary. And if we find evidence to the contrary, we are going to reject what the realtor says, and we are going to assume that the opposite is true. And the opposite in this case is that the population mean does not equal 1,560. So this is going to be our alternative hypothesis. So we'll label it H with a little a. So assume what the realtor says is true, look for evidence to the contrary. If we find it, we're going to get really mad, and we're going to reject what the realtor says. Sue him, fire him, throw a brick through his window. One of those options. So we go out and we do a little testing of our own. And we find our sample mean for average one-bedroom apartments in St. Louis. And it turns out to be, our sample mean is 1586. All right, and we talked to 50 people, 50 apartments, good, random, simple random sampling, good questions, no biases. And we know that the population mean of one-bedroom apartment prices in St. Louis is $100. All right, so that's what we come out with. What do we think so far when we come out with a sample mean of 1586? Are we like, yeah, I think the realtor was telling the truth? Are we like mad? Are we like, I don't know?
You think it's telling the truth?
We think it's telling the truth because it's close enough?
Yeah.
All right, Lisa's willing to give it the benefit of the doubt. It's close enough. It's 26 away. Anyone else have any other thoughts? So, how might we make this decision? So, assuming we're going to, we're going to assume what the realtor said is true. So, if it is, how likely is it that we would get a sample mean of 1586? Do we have a tool to tell us how likely that would be? So under this assumption that the mean is 1560, how likely is it that we would sample 50 people and get a mean of 1586? What's a tool we have to tell us how likely that sample mean would be?
T.
Z?
No, T.
T?
T.
Okay, yeah, those are pieces of it. Maybe something more general than that. It's a term you've heard me say a lot. Well, I'll give you a hint. The word or the term sample mean is in this larger term.
Sample distribution of the sample of the population.
Yeah, sampling distribution of the sample mean. So we have this tool we call the sampling distribution of the sample mean. Sampling distribution of the sample mean. And it is a frequency distribution of an infinite number of sample means. And what is the mean of this frequency distribution? The mean of the sampling distribution of the sample mean, what is it equal to? How much?
1586.
1596.
86?
1586. No.
100?
100? No.
I'm just guessing.
Guess what is the mean of the sampling distribution of the sample? You could tell me in this case, or you could tell me just in what's the definition? What's the definition of the mean of the sampling distribution of the sample mean? What's the most, so this is a sample mean. We're going to take samples of size 30 or more. What's the most common outcome for our sample mean?
1560.
Yes, 1560 is the correct answer. It's the true population mean.
Okay, sorry.
And the reason it's the correct answer is because we're assuming that this is the true population mean. The general answer is the mean of this is the true population mean. So our most likely outcome for our sample is the actual right answer. So it is the population mean, and in this case, because we're assuming what the realtor says is true, it is 1560. All right, and the standard deviation for the sampling distribution of the sample mean is the population standard deviation divided by the square root of the sample size. And we actually can calculate that. So 100 divided by the square root of 50, what's that come out to?
$14.14.
Thanks. Okay, so we have this sampling distribution sample mean has a mean of 1560, standard deviation of 14.14. How likely is it that any particular sample mean will be within one standard deviation of the mean? Percentage between 0 and 100? You know it off the top of your head? How likely is it that any particular sample mean that we take will be within one standard deviation of the center of this distribution?
Oh, 68.
68.4 or 3, I was
Yeah.
68.3.
3? Okay, 68.3. How likely is it that any sample mean we take will be within 2 standard deviations?
95.1.
Yes, we know all that. That's just a tiny fraction of what we know. We in fact know everything about the likelihood of any particular sample mean being any number of standard deviations above or below the mean. And this is a sample mean, right? This is one of those sample means we're talking about. There's a 68.3% chance this will be within 1 standard deviation of the center, 95.5% chance it will be within 2. So again, assuming what the realtor says is true, how likely is it that we get this outcome?
95.5. I mean,
All right, this one you do not know off the top of your head, but you can tell me the answer. How likely is this outcome? Well, we could put this somewhere on this distribution. It'd be like right here, it would be, 1586. We could determine how many standard deviations above the mean. It's not going to be 1, it's not going to be 2. It's not exactly 2,
Yeah,
right?
it's not exactly right.
It's not exactly 2, it's like 1 point,
it's within
No.
2, yeah.
it's like 1.9 something.
Right.
Yeah,
Alright, and then once we have that, then we could look at our z table, and we could get the probability. Remember in the first class we gave Michael Jordan a z-score? So Michael Jordan has a z-score of 2.3. And we said, now that we know his z-score, we know the probability of the next male who walks by being taller than Michael Jordan. We know that, oh, she's not taller than Michael Jordan. Yeah. Alright, so once we gave Michael Jordan a z-score, we knew the probability of anyone being shorter, anyone being taller, we knew the probability of someone being exactly that height. So we're going to do a similar thing here. We're going to give this sample mean a z-score. We're going to call it a z-stat, and we're going to know the exact probability of that outcome of a z-stat of that magnitude. So let's calculate that z-stat. So our z-stat, it's going to be the number of standard deviations this is compared to this. The number of standard deviations this is above this. So let's take 1586 minus 1560 divided by 14.14 equals 1.84. Alright. However you get the answer is fine. So 1.84. So there's a z-stat of 1.84. So this sample mean of 1586 has a z-score, z-stat of 1.84. Z equals this, and sample mean equals this. Alright, I would now like to know the likelihood of getting a z-stat of 1.84. How are you gonna find that formula?
That
in the Z
Z
table?
table? One takes one.
Exactly. Exactly.
So, 96.7%.
Alright, so my question for you, how likely is it that I get a z-stat of 1.84? And your answer is?
96.7%.
So that's pretty high.
Highly likely.
So that's highly likely that we would get a z-stat 1.84 standard deviations above the mean. Alright, so where I'm going with this is that's not too likely. 1.84 is not too likely because it's almost 2 standard deviations above the mean. It's not quite Michael Jordan being 2.3. Remember when we got Michael Jordan, there's like only a 2% chance of someone being taller than him?
Right.
So 1.84, it's not quite that extreme, but the probability is low. The probability of, maybe I'm not asking this question clearly. What's the probability of getting a z-score higher than 1.84? Yes, that's it. That's what I was looking for. So, the probability of getting higher is 3.3%. Okay. So we would say getting a z-stat at least that high, probability of that is 3.3%. You with me so far? Okay. Now, before we started this experiment, we didn't know if our sample mean was going to be higher or lower. We could have disproved what the realtor said 2 ways. One, with a really high sample mean. The other way we could have disproved it is with a really low sample mean. So this extreme z-stat of 1.84, of which there's only a 3.3% chance of getting anything higher, because we could have disproved this an additional way, we need to double this probability before we make the statement of how unlikely this was to happen. I know that's a lot of words. So we want to know how likely it would be for us to get a sample mean this extreme. And we know that getting a sample mean this high, there'd be only a 3.3% chance. But because it was a two-tailed test, what we'll call a two-tailed test, the null hypothesis could have been disproven 2 ways. With a really high z-stat, or really low z-stat. So we want to make this statement of how likely it is to get something this extreme, given our assumption that what the realtor says is true. In order to get to that point, we find this probability and we double it.
Doubling by squaring or doubling by adding it? again?
Multiplying by 2. So multiply by 2 and we get 6.6%. And we call that 6.6% our p-value. And our p-value is the probability of getting a sample mean at least this extreme, given a true null hypothesis.
Can you say the term 6.6% is a p-value, which means?
It's the probability of getting a z-stat, or a sample mean, probability of getting a sample mean at least this extreme, given a true null hypothesis. Alright, we'll spend a a bit more time on this, because I feel like I threw that last part especially at you quickly. So we'll just make sure we're feeling good about this. So, the realtor told us the average price of one bedroom is $15.60. We felt that realtor was a little shady, and we wanted to do some investigation of our own. So we said, let's give the realtor the benefit of the doubt, assume what he says is true, and look for overwhelming evidence to the contrary. If we find overwhelming evidence to the contrary, we will reject the realtor's statement and assume the opposite. So, we went out, we talked to 50 people, we found a sample mean of 1586, and we know the population standard deviation is 100. And then we asked the question, well, what is the likelihood of us getting a sample mean that extreme? If what the realtor says is true, what is the likelihood of us getting a sample mean that extreme? And if the likelihood is very, very low, we are going to assume that the realtor is lying. If the likelihood is a reasonable amount, then we'll say, okay, fine. Mr. Realtor, we believe you. So if the likelihood of getting something that extreme might be 25%, there's a 25% chance that when we go out and sample, we would get something that different from what the realtor said, then we would say, okay, all right, that's fine. There's 25% chance of that happening. We're not going to throw the brick through your window. We're not going to assume that you're wrong. We're not going to sue. We're going to say, this happens. We get sample means that can be this different from the true population mean 25% of the time. If, on the other hand, we get something that's rather unlikely, like maybe something that only happens 6.6% of the time, now we're going to say, well, Mr. Realtor, this is so unlikely to happen. Rather than believing what you say is true, I'm going to say that what you're saying is not true. You with me?
Well, I'm just confused in that. Are we saying that the 1586 is the unlikely to be true, or the 1560 is unlikely to be true?
The 1560 is unlikely to be true.
Okay.
That's a good question. We are assuming our data is good.
Okay, so we're assuming that our sampling of the 50 people is the real.
We're not saying it's the real population mean. We're just saying it's a good sample.
Okay.
So we use the proper sample size, and it falls in a predictable way on the sampling distribution of the sample mean. So if this is the true mean, then we could still get a rather extreme sample mean. It's possible. We could get anything along this frequency distribution. We could get something really, really high, we could get something really, really low, or we could get something right in the middle. And there's a chance of any outcome. There's definitely a chance of this outcome. But the thing we're thinking about here is we're asking ourselves, what are we willing to believe? If we get a sample mean that is so far into the upper tail under the assumption that the realtor is telling the truth, then we have two choices. We can say, well, that happens a very small percentage of the time. That's one option. We can say, all right, what the realtor said is true, mean is 1560, the mean of the sampling distribution of the sample mean is 1560. Something this extreme happens a small percentage of the time. That's certainly a valid option. What's our other option?
That it's not 1560.
That it's not 1560.
It's higher than that.
That this whole model with the sampling distribution sample mean of having a mean of 1560 is not true.
Right.
we're just going to reject that that is true. So we have two options. We believe something that is very unlikely, which it could happen, it's just unlikely, or we reject what the realtor is saying and we say that the null hypothesis is not true. Question?
So is that because the number is so, like it's closer to that number? Like I'm trying to understand, like I get, you don't want, it should be a higher percentage then, right? So it's supposed to be in the middle. So if it was like 18,000, then 33.3% means that it's closer to the other side, like the mean?
I'm not sure I'm following.
Okay.
Where'd you get 18,000?
No, I'm just saying as an example, like you want, since the numbers are so close, it should be a higher percentage to the,
But I think the best way to think about it is on the sampling distribution of the sample mean, what is the likelihood of this outcome?
Very little.
Alright, specifically what is it? What's the likelihood of getting a sample mean at least this extreme?
3.3%.
Remember we have to do the double
Oh, yeah, the
thing.
3.6%.
6.6%. Alright, so the chances of getting an outcome this extreme, 6.6%. So,
That's low.
it is low,
Yeah.
but you still have a choice. You could believe the realtor or not believe the realtor.
But in our case,
But
we're
ours-
rejecting the null hypothesis.
Well, we haven't fully decided that, but let's decide that right now.
Yeah.
Are we willing to believe something that is only 6.6% likely to happen?
No.
What's your threshold?
Yeah, what's the cutoff?
Yeah.
Over getting.
Ileana, what you tell me, what's your threshold of what you're willing to believe from this realtor? If it's 6.6,
percent is too low.
it's too low? Okay, what would be your cutoff? Would 10% be a good cutoff for you?
No, I want
I
to
feel like it should be more.
Right? I want to be 60.
Oh, you think
No, but I mean, if it's more than 50%,
Oh, so
then it's less.
okay, so
Yeah,
50% would be
60%.
your
Yeah,
cutoff?
'cause that would be.
You want something that is, okay, yeah,
Yeah.
you want 50%. So that would be, I mean, let's just think about this. If it was just one standard deviation above the mean, that would mean, I don't know, I think I'm gonna confuse myself and confuse you if I start going down this road.
Yeah.
Let's just say that our threshold, our cutoff for what we're willing to believe is 10%. And we're gonna call that our significance level. We're gonna say anything that is less likely to happen than 10%, we won't believe it. If it's more likely to happen than 10%, then we'll say, okay, fine, we're a little suspicious because our sample mean was higher than you said, but we're going to not throw the brick for right now. So our significance level, our threshold for what we're willing to believe is anything above 10% likelihood. If it's less likely to happen than 10%, we are going to reject the null hypothesis. So the realtor told us the average rent was 1560, our sample mean was 1586. What's the likelihood of us getting this sample mean given what the realtor said is true?
6.6.
6.6? Is that below our threshold of what we're willing to believe?
Yeah, so I would reject.
Reject the null hypothesis, exactly. Okay. Yes?
So, if it's like maybe, okay, what if it was like 9.9?
Yeah.
Would you not accept?
I would accept it.
If it was 9.9,
Reject?
we would reject.
You would reject still, okay, when would you not accept?
Anything over 10.
Well, there's only two options, we reject or we fail to reject.
Fail to reject, okay,
Okay, so if it's 11%, if this came out to be 11%,
yeah,
fail to reject.
fail to reject, okay.
Or accept.
It's not.
Well, statisticians don't like saying accept,
So it's reject or fail to reject.
reject or fail to reject.
I know.
And fail to reject is
Fail to reject.
it means we're not saying the realtor is telling the truth. We're not saying that. We're just saying we don't have enough evidence to prove that he's lying.
Oh.
So we fail to reject.
Okay.
We're not saying you're telling the truth.
You sound like a politician.
Well, glass is so half empty. Reject or fail to
I see
reject.
it.
Okay, so we failed to reject.
Above 10.
Above that.
Above 10, we fail to reject. Yes. Okay. So let's answer this same question a slightly different way. We knew that this z-stat of 1.84, that fell into what we'll call a rejection region. All right, that was a z-stat that was too extreme for us to believe given our 10% significance level. So let's find out what the cutoff point would be for z-stats, both positive and negative. So if our significance level is 10%, we're willing to believe anything that is more than 10% likely to happen, but we're not willing to believe anything that is less than 10% likely to happen. And we know, on this sampling distribution of the sample mean, we know how the data is distributed. And we know that a certain percentage of the data is in the upper tail, a certain percentage of the data is in the lower tail. And if we're willing to believe anything that is 10% or more likely to happen, and we're not willing to believe anything that is less than 10% likely to happen, then in this particular case, we're going to divide that 10% in two, and we're going to say anything that's in the 5% tail down here, or the 5% tail up here, we're not going to believe it. 5%, 5%. Okay, so everything's still the same. Our assumed mean of this is 1560. Mean, sampling history of the sample mean is 1560. Alright, we're assuming that's true. If that's true, what would be the cutoff point for the upper 5% and the lower 95%?
That was 1586.
What's that?
That was 1586.
We're assuming what the realtor said is true.
Oh, okay.
So if the realtor is telling the truth, then the center of this distribution
It's where
is
it's-
1560.
Got it, okay, sorry.
Yeah.
Keep going.
So,
45.
alright, so we need, what I want now is the z-value that separates the upper 5% from the bottom 95%.
So 1.65.
Yeah, that sounds right to me. 1.65?
1.65, yeah.
And what's the z-value that separates the bottom 5% from the upper 95%?
Negative 1.65.
Excellent. Alright, so we're going to call these our critical values. Critical values. Alright. Positive 1.65, negative 1.65. So, anything above or below the critical values we'll call our rejection region. Reject. And here, reject. Alright, so anything that has a z-stat of greater than 1.65, reject. Anything with a z-stat of less than negative 1.65, reject. And what is the z-stat in this case? 1.84. So where does it fall?
Above.
Falls into our rejection region. Any questions?
Is that a standard number that moving forward in all statistics that we'll use?
For
Is one for
significance level?
Yes.
Yeah.
It is not. We will decide our own significance level when we're doing our own tests, or the significance level will be given to you on the questions that you do in the textbook. But let's look at a couple other significance levels. Suppose, and actually I think the text has a significance level of 1% for this example, 0.01. Alright, if the significance level is 0.01, let's make our reject or fail to reject decision, and we'll do it two ways. First, let's look at our p-value of 6.6%. So, with our significance level of 1%, we are willing to believe anything that is greater than 1% likelihood. But we are not willing to believe anything less than 1% likelihood. So that's our cutoff point. Anything less likely than 1%, we will not believe it. If it's more likely than 1%, we'll, kind of believe it. We'll go along with it, we'll just say. So what is our reject, fail to reject decision if our significance level is 1%?
What region of it is?
The p-value is 6.6%. Our significance level is 1%. What is our reject, fail to reject decision?
We feel
2.33.
It's easy, you're gonna tell me either reject or fail to reject.
fail to reject.
Fail to reject is correct. Alright, it is not extreme, it's not unlikely enough for us to say we reject. It happens 6.6% of the time. And we're not gonna reject until we see something that is so unlikely that it happens less than 1% of the time. Alright, if that confuses you a little bit, let's do that with the critical values, and I think that'll shed some light on it. So if our significance level is 1%, what in that case would be our critical values? So significance level is 1%. We need to separate the 0.5% of data, 0.5%, 0.5%, the upper 0.5% of data. So what separates the upper 1/2 of 1% of the data and the bottom 99.5% of the data?
0.52.
No.
Oh, no, I'm sorry. 0.005.
I'll give you a hint, it's gonna be a number higher than 1.96.
2.6.
Are you just guessing?
No, sorry. 2.62.
No, 2.6 is 0.9953, so I think that's closest.
I like,
2.33?
I could go along with 2.33,
That's what I said.
is that right? 2.33?
I thought we were looking for 99.5, no?
What's that?
We're looking for 99 or 99.5.
0.5, 99.5.
So it's 3.36.
It's what? 3.6?
2.57.
2.5?
Okay, look, 2.8.
I feel more comfortable with 2.58.
Eight.
Chris, can you go along with 2.58?
Sure. 0.9951.
Yeah, were you looking at the wrong thing? We're 2.33?
Yeah, I was looking for 99.
Oh, you're looking at 99? Okay, yes, okay. So 2.58. Alright, positive 2.58 and negative 2.58. These are going to be our critical values with a 1% significance level. Alright, let's just run through this again. So, remember, the realtor told us the average one bedroom in St. Louis was 1560. We thought the realtor was shady. We wanted to do some research of our own. We went out, sampled 50 people, found a sample mean of 1586. Standard deviation, well, the whole population was 100, was no. So he said 1560. We found 1586. That's different. The question is it different enough for us to say that the realtor's lying? Well, how would we be able to know different enough? Well, it turns out we have a very good tool for determining how likely this outcome would be if this is true. And what is that tool? Sampling distribution of the sample mean. We know, because this is normally distributed, that we can determine exactly how likely a sample mean of 1586 would be. And getting that high would be 3.3% likely. And since there were two ways to disprove the null hypothesis, we could have gotten a really low sample mean before we started this question. We double that, and we say our p-value, 6.6% chance of something that extreme happening if what the realtor said is true. And then we compare that 6.6% to our significance level. And if our significance level is 10%, meaning we are not willing to believe anything less likely than 10%, we reject the realtor's null hypothesis. If our significance level is 1%, right, then we have a very high standard before we reject what the realtor said.
We would fail to reject.
So we fail to reject because 6.6% is higher than the significance level. All right. Let's do a exercise. Let's do number 32 in chapter 9. Sometimes acts funny. Does anyone have their textbook with them? 32 in chapter 9.
Yes, suppose you're testing the following hypothesis. The null hypothesis is
1,000.
u equals 1,000.
Sample size is 36.
No, number 32, the population mean is 1,000. Sample size is 81.
81.
The sample mean is 975.
Yeah, 975, right.
Conversion, it's just the numbers from the.
I have an intentional. That was part of it. Hey, you want to stop for you? So what page are we on?
It's 335. Number 32.
So do we have to bring it like every 8 months?
Yes.
That's the one we left off.
Sample size.
sample?
Eighty-one. Oh, no, sample mean is 995. Sample size is 81. Standard deviation is 90.
5%, yeah. The 100 is the standard deviation.
Here's mad now, what should we-
Where's each one?
That's gonna work.
That should be,
Over the square root of 81. Do that, what you like, 2.5 minutes. And then,
hold on, you big square there. I did, right? That's how you find the difference?
yeah, but you have negative 2.5. That's what you have. How many is it saying?
I forgot the formula.
Which formula?
It's the standard deviation divided by the square root of the sample size.
You got a Z stuff? Or should have, yeah, that, but
Alright, ready to do
my
it as
number
a class?
is, you got a negative number?
Alright, so our null
Yeah,
hypothesis
2.5.
is that population mean equals 1,000. We're gonna assume that to be true, unless we find overwhelming evidence to the contrary, in which we will assume we will reject the null hypothesis, and in that case, we will accept the alternative hypothesis. Significance level of 5%, that means that's our threshold of what we're willing to believe. Anything less likely than 5%, we won't believe it. Anything more likely than 5%, we're like, okay. So we do some sampling of our own, we come up with a sample mean of 975. We ask 81 people, population standard deviation of 90. How do we calculate our Z statistic for this sample mean?
So you do this
The
90
standard deviation.
divided by, right?
The square root of the sample size.
So what's our formula here?
90 divided by,
90?
yeah, right?
Well, we want the difference first, right? We want the
Oh,
difference
oh.
between these two.
But how do we get the difference if we have to divide it by the
So we take the 975 minus 1,000.
1,000, yeah?
Yeah, so we want to know how many standard deviations of difference there is. So definitely on the right track, you're calculating the standard error, or standard deviation of the sampling distribution of the sample mean. We want to know how many of those encompasses this difference. So 975 minus 1,000 divided by, what, Marie?
Standard, the
90,
10.
Yeah, 10, so it's 90 divided by the square root of 81, which is 10.
oh, because you did that example first and then you divided it by it, the last one.
Well,
Not
before
sure.
you
Put it all
had
together.
the standard deviation of the population mean, right? When you did, data with this
Yeah.
sub X bar, that's what we did before, which is
Yeah.
the denominator in this equation. And when we first started
So
class,
we just did that, and then we got that
Put it
number,
all
then
together.
we minus net 75 divided by.
Because I calculated it out for, Dan told me 14.14,
right.
and then I just put it in here.
Yeah, yeah,
Right, that's, I think
That's
where the
why.
confusion was.
Okay.
Yeah.
Alright, okay, good. Good, so,
Okay.
good point, glad we straightened that out. So. What?
So you get negative 2.5.
So 2.
Negative 2.5,
Yeah.
Susie?
Yeah.
No, negative 3.
Negative 2.5.
Negative 2.5, alright. So, we've got a z-stat of negative 2.5. My question to you is, how likely is it we would get a z-stat that extreme?
Oh.
0.5.
What's that? How likely is it we would get a z-stat of negative 2.5?
1.96.
How much?
1.96.
I could go along with that. 1.96%? A little less than 2%?
Oh, times it, got it. Times it,
No, it's times
Let's see the table on that.
So it's negative 2.5 and then positive 2.5. So it's really 5, right?
It's 9. And we bring down the.
Okay, so what is the likelihood, so what is the area to the left of the negative, of a z-stat of negative 2.5? How much area is in this lower tail? Now, if you have the negative z table, you can just look on the negative side for negative 2.5, and it will tell you some very small number. 0.0062? Okay, that's right. 0.0062. So that is about 1/2 of 1%. Now, this is what we'll call a two-tailed test, because there are two ways to disprove the null hypothesis. And before we started this sample, we didn't know if we were going to get a mean that was really high or really low. So in calculating our p-value, what do we need to do to this?
Double.
Double it. So our p-value is going to be 0.0062 times 2 equals 0.0124?
Yeah.
Okay, so 1.25%. So our p-value is 0.0124. Now we could make our reject or fail to reject decision.
You got, I'm sorry, you got the 2 from the Z table?
The what?
The 2? You see how you got the 0,
This
6,
2?
2? Yeah.
This 2 we double
We double.
this number. The reason we doubled this number is because we have to account for the other possible extreme outcome
Value.
of a really high
Yeah,
Z
and it
value.
would also be like a 2.5 underneath it, but just positive. Yeah.
It could, well, we double the, I guess you could do that, you could just do the positive and negative side of this.
Yeah.
The statisticians don't really do that, we won't do that in our textbook, but I guess you could. You could say the probability of negative 2.5, the probability of 2.5. Yeah, that, I mean, that's,
Yeah, because if,
I do not fault you for that logic, that's
That's the way
good.
my showing me.
Yeah,
oh yeah, because of it, on the positive side, the z-score is 0.9938.
okay. Okay, so we get this value, we double it, and we get our p-value of 0.0124. Are we ready to make our fail to reject decision?
Yeah.
Go for it, Marie.
Just one more question, are you always gonna double it?
If there's two ways to disprove the null hypothesis, then we'll call it a two-tailed test. In that case, we'll double it. If there's not two ways to disprove it, we will not have to double it. Go ahead, Marie.
So it's less than the significant level, because it's 1.24%, and we have a significant level of 5%. So we reject.
Reject, yes, yes, yes. Fantastic, fantastic. We reject. Now.
And we reject you.
Alright. Any questions on this? Let's do our critical values. We just did this with the p-value version. What would be our critical values? And we know that negative 2.5 is not, or it is extreme enough, so it's going to be something inside that negative 2.5. Let's determine those. Did anyone get those?
Hold on.
So for our critical values at 5% significance level, we want the 2.5% in the upper tail, 2.5% in the lower tail.
Hold on. Which is, oh, 1.65 positive.
I don't know if I'm liking 1.65.
1.96.
So is it 2.5 or?
Can someone give me a bold answer?
1.9. Yeah,
How much is it?
1.96?
1.96, I like 1.96.
Yeah.
Alright, negative 1.96 and positive 1. Alright, so our critical values would be negative 1.96, positive 1.96. If we get a value that is more than 1.96, we reject. If we get a value that is less than negative 1.96, we reject. And we got a value that was negative 2.5, negative 2.5. So, as Marie pointed out, we reject the null hypothesis. Make sense?
Yeah.
Okay. Let's move on to a one-tailed test. Right. All right. So suppose instead of telling us that the mean rent was $15.60, the realtor told us that the mean was less than or equal to $15.60.
Yeah.
So we're in this realtor's office and the realtor says, you know what, we've got great real estate prices in St. Louis. I can get you a great deal because the average one-bedroom price is less than or equal to $15.60. So the realtor is just making a different statement. He's not saying it's equal to $15.60, he's saying less than or equal to $15.60. So again, we get a bad feeling about this, but we want to be scientific about it. We want to jump to conclusions. So we say, let's assume what the realtor says is true, that the mean is less than or equal to $15.60, unless we find overwhelming evidence to the contrary. And if we do, we're going to assume the opposite, that the mean is greater than $15.60. Okay. So we're going to look around for our sample mean. Let me ask you a couple of questions. Suppose we find a sample mean of $1,200.
Great.